Hey, welcome back. It's week 5, lesson 2 for physics, and this is the day we discover radiation. So we're going to talk about what radiation is, the three different types, and also the history of it and some characteristics of radiation. So let's start off with something that's not really radiation at all, but X-rays. Roentgen discovered X-rays in 1895. He had a cathode ray tube, which is the same thing that used to be in the old TVs. It's not in your TVs you guys have today, but when I was growing up, as an RTV. And what he noticed was when he turned on this high voltage cathode ray tube, it made these crystals that he had on his desk or another part of the lab sort of glow weird. And he's like, wait a minute, how is that happening? And he went on to study what these special rays were. So it was invisible energy. And it's really the famous picture of his hand that he took. He put his hand over some photographic paper, and then it was either his hand or his wife's hand, I don't remember. And then he put the X-rays, and the X-rays penetrated through his hand and left the image of the ring in the hand. All right, now that isn't really radiation, though. Another guy, Henry Becquerel, was studying. Now it says phosphorescence here. I might have a little misprint there. I always thought it was fluorescent rocks, and you know what fluorescent is. Fluorescent is like the hunter orange. It shines up. When you look out across the field, you can see the hunter way out in the field, especially at sunset, when the sun's going down, but it's still some little bit of light out there, but that vest really glows. If you're at a track meet, it starts getting dark, and the people with the bright yellow shoes, they glow. They look like they're almost producing their own light. And that's because fluorescents do produce light. When light rays hit them, they give off their own ray. It excites the electrons. They jump up a level, they fall back down, and they give off this extra light, and that's what we see. All right, so that's fluorescent. I don't believe it's supposed to be phosphorescent, so that should be fluorescent there. And he was studying uranium rocks, and he was trying to take a photograph of these, and he places his uranium rocks on top of the paper, which the photographic plates, which were in paper, it was light proof, so they were safe, he thought. And lo and behold, what happened was the uranium's producing this invisible light that could penetrate through the paper and expose the films. And so after he noticed it darkened the film, he said there is some kind of invisible ray coming from these rocks, and it's exposing here. And here's a picture of him, and then here's all the actual photographs, and this is where he had the rocks, the uranium rocks, sitting on top of his plates. Right? And they still use this kind of thing to test for radiation today. They use a little photographic some film, unexposed film, and then they look at it, and if it has little speckles on it, then they know that it's been hit with radiation. Okay, so now, why is that different than what the X-rays? It's because these just came from a rock without a power source. The X-rays, it took a power source to make it, right? So they were producing this energy and producing rays. Here, this came out of nowhere, just out of these rocks. All right. Well, some other famous people here that you probably have heard of. Marie Curie and her husband Pierre. Now, Marie was a physicist and Pierre was a chemist. And so they were working together. What? You got a bike right now? Can you wait till I'm done? I only take a few minutes. Frank? Okay, we're going to talk about two people you probably know. Marie Curie. Marie Curie and her husband Pierre. Now, Marie Curie was looking for something to write her doctorate on, and and Becquerel had just discovered radiation, and she was pretty intelligent. She said, "Well, I'm going to study something that no one has really studied before," and so she takes up the study of this new radiation that was just discovered, and she starts working, and her husband was Pierre Curie. He was a chemist. She was a physicist, and so they kind of work together. But she does most of the work, and she goes on and discovers two different elements that from these uranium. She finds all the uranium ore she can find, and they start to isolate it and try to find different things. And one of those things they find is radium. And radium was so radioactive. It was like 100,000 times more radioactive than the uranium was. And it was so radioactive that it used to glow in the dark. And so, this was before they knew anything about radiation. So they didn't use any protective gear or anything. And the radium would just glow, and they would handle it with their bare hands. This later came back and caused a lot of problems for Marie with cancers and stuff in her hands. And another thing that happened with this was that watchmakers picked up on this radium that glowed in the dark, and they thought, "Oh, this is great." Now, they call this phosphorescence. Phosphorescence means that it glows afterwards. So fluorescent, it glows when light hits it. Phosphorescent then gives off light later on its own. So this is phosphorescent. And so the watchmakers would paint the hands of the watches like this, and then they could finally see the time at night, right, when it was dark. And that led to terrible cancers and things for the people who actually painted the watches. There's a movie about that I saw. I haven't seen the movie, but there was I saw when I was looking this stuff up. There's a movie. I haven't looked at it, so I can't give any recommendations for it. All right, so she went on and found another element and named it after her home country of Poland. So that's where radium and polonium come from. And so she was the first woman actually to win Nobel Prize for physics. And she went back and she won two. The first Nobel Prize, Marie, Pierre, and Becquerel all got together. And then she received another Nobel Prize on her own later. All right. So let's just talk about what this radiation actually is. There are a few different types of radiation. Now, we're going to call this radioactive decay. And that's because the atom, the nucleus, is going to break apart. On its own. It will spontaneously break apart into these other pieces, right? Small little pieces will fly out and it'll break apart. The first type we'll talk about is called the alpha particle. Now, the alpha particle symbol looks like a little fish, right? Greek letter for A is alpha. It looks like a fish. And the alpha particle, that's a symbol right there, has a mass of 4. 4 atomic mass units, right? And the reason it has a mass of 4 atomic mass units is because it is made out of 2 protons and 2 neutrons. All right, when we look at that, what do we see? We see 2 protons, we see 2 neutrons, and automatically in your head you should be saying, oh my gosh, that is a helium nucleus. All right, Teddy, you're too loud. Get outside, go, come on. Okay, sorry about that. The dog is super loud, almost as loud as my wife when I'm trying to make these videos. And so that's the same as a helium nucleus. And what will happen is that it's a large atom, it's unstable, and so it starts to break down and fall apart. And what happens is this four particles together, stuck together, shoot out, and that's what we call an alpha particle. All right, and it's the same as a helium nucleus, so it has a charge of +2. It has a mass of 4. It's the same as a helium. All right. Now, I'm going to put this into a chemical, not a chemical equation, into an equation. This is a nuclear equation. All right, and I have an example here. Let's look at this little teeny example first, and then I'll put this into an equation. So we have uranium-238. Uranium-238 is your average uranium, right? There's a uranium-235, there's uranium-238. This is the less radioactive of the two. All right, and then uranium goes through this decay. Now, we're going to write it like this. So start with a U. 238 goes on the top because that's the weight. 92 goes on the bottom because that's the atomic number. Right? If you do the math, you can see that there's 146 neutrons there. 238 minus 92 equals 146. Okay? Now, we're going to show this decay by drawing an arrow. So it looks kind of like a chemical equation. Right? And I'm going to start off with the alpha particle. Now, there's different ways of writing this. If you would like, and this probably makes the most sense, is since the alpha looks like a helium, you write the symbol for helium, and you put 4 on the top because it has a mass of 4, and 2 on the bottom because there's 2 protons. Okay. Now, sometimes people, and I have this down below here, I know this isn't where it's supposed to be, and I'll erase it in a little bit, but you could probably write the alpha particle 4 and 2 like that also, and that would be acceptable. So either one is fine. I'm going to go with the atom. Okay, and what else does it do? Well, what happened? We lost 4 nucleons. That means we lost 4 particles in the nucleus. That's what makes up the weight. So we lost 4 particles, so that means that we have 234 particles left in that nucleus. All right, I just subtracted. And then we had 92 protons, and we lost 2 of them. So that means we have 90 protons left. Okay, we're almost done. Now what you need to do is go onto your periodic table and look up what element has 90 protons. So you go through the table and you look at the bottom here, and I have my table beside me, not so you can see it, but you look and you see that thorium, TH, has 90 protons. All right, and we're done with the particles. Now what happens when anything breaks down the atom, it also gives off its extra energy in the form of gamma radiation. Now, gamma radiation is not even a particle. It's a kind of light, right? High energy light, even stronger than X-rays. And so its little symbol, you can just put change in energy if you'd like, or you can use the gamma symbol, which looks like a little fish this way. All right, and that is your reaction. That's an alpha reaction. All right. I'm going to move this. Watch this. All right. Put that, oops, whoa, it's upside down. Put that right there, and that's in a good spot for it. Okay. This is in smoke detectors. You guys can read this yourself, but they use this technology in smoke detectors. The alpha particles somehow take away the electricity when the smoke comes in, and it causes the alarm to go off. And so they use different things. They use radiation for things like that all the time. All right, role of neutrons. Okay, now, what do the neutrons do for us here? The neutrons are going to be spacers. Look how big that atom is. Now remember what happens when you have electromagnetic energy. I'm going to put EMF, electromagnetic force, right? It's a build-up force. It builds up, right? We had that Van de Graaff generator going, and the longer it was on, the bigger you could feel that area. All of a sudden your hair started to stand up. You could feel it around you. It builds up. Well, the same thing's happening in this nucleus. Those protons are adding up. There's more and more protons. There's 92 protons. And those 92 protons, if another little particles on the outside here, so I guess the pink is they start pushing, right? They're getting pushed out. And so if you have 90 against those two in the alpha particle, eventually it's going to push it out of the nucleus, and the nucleus will actually change into a different element. Okay, another name for this is transmutation. It's changed into something different. All right, so that's our first type of radiation. Our second type of radiation is called beta, right? Alpha first, beta second. All right, so the beta, the symbol is a capital B. It's a Greek capital B, right, with a little tail on it. The mass of a beta particle is the same as electron. So for the same as electron, it's very, very small, right? We don't even count the mass of an electron when we're talking about the weights of atoms. So it's very, very small. And its charge is the same as electron, is -1. And its equivalent particle, if you haven't guessed this yet, is an electron. So a beta particle is an electron that's being shot out of the nucleus. I'll say that one more time. A beta particle is an electron that's being shot out of the nucleus. Now, if you're thinking to yourself, that sounds weird, that's because there are no electrons in the nucleus, right? And all of a sudden this particle, a beta particle, gets shot out of it, which isn't even there in the first place. Okay, so what that has happening, and this is not the real way to think of this. This is the incorrect way, but it helps people at first. A lot of people think that, oh yeah, all that's saying is that, we know that a neutron and a proton are about the same. The neutron weighs a little bit more. So we'll say this is a neutron. Whoop. So maybe a neutron is just a little teeny electron and a proton that have been jammed together. And you can think of it that way. It's not really the way it really is. Remember, the neutron and the proton are made up of those quarks. And what happens is that usually this happens after if energy hits it, okay? And so energy is going to hit this thing, and it's going to cause that neutron to change. And there's actually two particles that are going to fly out. One of those particles is the beta particle, which is the electron. And the other is an antineutrino. Okay, now antineutrinos are nothing that we're going to worry about. It's just going to make it more complicated. All right, but all you have to know is that those quarks inside that neutron change. And they lose particles and they change how they are. And the next thing you know, that neutron has turned into another proton. And at the same time, an electron has been shot out. We're going to ignore the antineutrino for right now because we don't want to go there. Okay? And so what happens is, if you look at this, let's write the equation here. I'm going to do it in the right spot this time. I think I'm going to do it in purple. So we're going to start with carbon 14. So carbon 14, 14 and 6. So it weighs 14, it has 6 protons, that's carbon. And it's going to go through this beta decay. So let's start the same way we did before. We drew helium nucleus, right? This time we'll just draw an electron. Okay. Now, the electron has almost no mass. And if we want to keep it the same way, we can put -1 down here, but that's not a negative proton. That just means it's an electron charge, okay? So you might want to ignore that. Plus, all right, what's it going to do? So does the mass change? Well, before we had carbon 14, there were 14 particles, 14 nucleons inside that nucleus. We lost an electron that has 0 mass almost, right? So we still have 14. We still have a mass of 14. It's only lost an electron mass-wise. But the thing that has changed is one of those neutrons, remember, has been changed into a proton. So what happened to the atomic number? It was 6, now it's 7. Look on your periodic table. What has 7 protons? Nitrogen. Plus that gamma radiation is given off. All right, so a little bit different there, right? So this time the mass isn't going to change, but the number of protons goes up when this happens. All right, why would these two different radiations be different? Alpha radiation, the atom's too big. Right? There's too many parts on there. It's too big, it's unstable because there's too many particles. And it shoots out particles that make it more stable. All right, beta. Why is beta? Well, remember we said there was a balance between neutrons and protons. Those neutrons on smaller atoms aren't as important because they don't need them, right? The neutrons are to spread out the nucleus. It doesn't want extra. You don't need extra. You don't need more people to do the same job, right? If you have enough people to do the job, extra people are just in the way. Think of it that way. So we have carbon 14 that has these extra neutrons it does not need. What's the best way to get rid of neutrons? Well, convert those neutrons into protons. Seems to be the way nature has decided to take care of this. And so now we have fewer neutrons, and our neutron-proton ratio is back to 1:1 for that smaller atom, which is where it wants to be. Okay, I hope that makes sense. So your beta and your alpha reactions will follow those same patterns. There's going to be some in the homework. You know, follow those patterns, and it should be fine. All right, gamma. All right, now gamma has no mass. Not almost no mass, because it's not a particle. It's a form of light, right? It's electromagnetic energy. This is the nasty stuff. This is the stuff that causes the cancer and it penetrates through everything. It's dangerous, right? Things where you go in outer space and it fries you. This is gamma, right? It has no charge. It's not a particle. It doesn't have a charge. And it isn't a particle at all, so it doesn't have an equivalent particle. I just copied and pasted. So it's electromagnetic radiation, right? So it's a form of light. Right? But it's very high energy light. So this is the dangerous stuff that causes cancers and things, and we'll talk about that stuff later. All right, let's look at penetrating power of these radiations. I found this little picture and I thought this was nice. Okay, so here's an alpha. The alpha particle is big. The bigger the particle is, the slower it goes, right? So it doesn't move that fast, and it has a large mass. And so you can actually stop an alpha particle with a sheet of paper. It can't penetrate paper, It can hit your skin. It can't penetrate your skin, but it can hit your skin, maybe cause damage on the outside, but it's not radiation that's going to penetrate through your whole body. Okay, beta particle. Beta particle, same as electron. It's moving pretty fast, so it can pass through a sheet of paper. It can pass through you, but you can stop it with a sheet of aluminum. Usually they have aluminum here. This just says metal, but a sheet of aluminum will stop it. So that's where you put on your tin foil hat. There you go, your aluminum foil hat. That will protect you from those beta radiation. This isn't really a form of radiation, but it was on the list. They had one without this, the same thing, but I thought this was interesting. Remember, this has no charge, it's a neutron. If you could shoot a neutron, because it has no charge, it's not going to repel or attract anything. And so neutrons can pass through paper, through your hand, through metal. Water slows it down, though. Water does a good job of slowing it down. So this is going to come to play later in nuclear reactors. They use water to moderate or slow down the reactions. All right? And our final thing is gamma radiation, and this is the highest energy form of light that we have, and it's intense, and it can pass through paper, humans, aluminum, water, even thick concrete, but it's usually stopped by lead. So this is the stuff that people were trying to build the bomb shelters to protect themselves from, right? This is why when you go into, it would also stop x-rays too, right? But you get x-rays or any kind of medical stuff done, they give you a lead vest to protect your baby makers and keep your reproductive organs away from radiation, because those organs are producing cells all the time, and you do not want any kind of mutation. So that's why you wear that lead vest when you go get an x-ray. Okay? All right, let's go through a few terms. All right. Radioactive isotopes are the isotopes that will decay. They will decay on their own, and it varies depending on what the material is. When an element changes from one to another, and that's through decay, right? It changes from, like we just changed carbon into nitrogen, right? That's transmutation. It's changing into something else. Okay? The parent nucleus is the one you start with. Right? So we started with carbon, it turned into nitrogen. Carbon would have been the parent. The daughter nucleus is the one that it turns into. And so nitrogen would have been the daughter nucleus. Now, all these elements follow a predictable decay pattern. If it's radioactive, like any other element, it's going to break down in the same pattern because they're the same element and they're the same isotopes. So if you have uranium-238, it's going to follow a pattern. And this is called the decay series. Now, if you look at this, when it goes down, now look at the chart. This is the masses on the side. So we have masses over here. And this is the atomic number. So as it goes through the chart, I'm going to trace this in maybe, let's do it in bright pink. And so as we go from uranium through an alpha decay, it drops atomic number, drops by mass by 2, right? An atomic number, I'm sorry, I said that backwards. It drops in mass by 4 and atomic number by 2. So it goes down like that. And as we go through beta decay, then beta decay increases the atomic number, but the mass stays the same. So there's 2 beta decays. And then we're going to go back down. Alpha drops 4 in mass, 2 in atomic number, drops 4 in mass, 2 in atomic number, 4 in mass, 2 in atomic number, drops 4 in mass, 2 in atomic number, drops 4 in mass, 2 in atomic number. Now we're doing some beta decays. So it stays the same mass, increase atomic number, increase atomic number. Here's another alpha, beta, beta, alpha. And then, so uranium-238 is going to follow this each time. And when it's done, it's going to end up being lead. Right? Lead-206. Now that means lead has a mass of 206. So if I was going to write it my other way, I'd write Pb 206 on top, and then Pb, if we look up its atomic number, it's 82. And that's where uranium-238 is going to go. If you look on the chart here, here's the time periods where this happens. And these are called the half-lives.
Okay, we're going to call that a lesson right there. The part that I want you to turn in, of course, you have to do the questions on the back. So yesterday's lesson, or part 1, was the parts of the atom, is 1 through 12. And then today we talked about the discovery of radiation. That went all the way through problem 24. So those are your 2 written assignments. And again, you should follow along with the notes as we took these notes. Hopefully, as you went through today, you wrote down what we said, so that way you can answer the questions. And then if you will just forward those to me, or take screenshots, whatever you need to do, so that way I can get your grade in the book. Probably the easiest way to do the problems at the end, the questions, are most of them are like written things. There are some things you have to write, but maybe you could either write them out on paper, or you could type them up in Google Docs. Again, if you're going to answer with print, if you change the color of your font, it will make it a lot easier for me. Thank you very much. Have a great day.